All right, why don't we get started? Please excuse my sniffles this morning. Um, have a bit of a cold. It is cold and flu season upon us. So we have homework 2 due next week on the 29th, and that is an exercise from the book that requires you to use fork and exec. I expect you to use sources that are out there on the internet. There's plenty of reference material, but please make sure you understand what's going on because we're going to build on that assignment going into the future. Okay. Any questions about this? No? All right. So where we last left off, we talked about message passing, and we talked about the physical implementation, and we talked about the logical implementation. And in particular, we're talking about the communication link used by two cooperating processes to interact with one another. And from a physical standpoint, you can back your communication link in a number of ways, one of which is shared memory. And we'll see an example of that today in practical terms at the command line through an example. So shared memory, we have the hardware bus. And so with the hardware bus, you can imagine you have two processes, and maybe they're on two different CPUs on for the same system, and they literally create a channel of communication, or rather the operating system does, using the system bus, right? So in that regard, you're going to send data directly over the bus to that other process that's residing somewhere in another CPU. And then there's the network, of course, that involves I/O controller for the network card, and that implies you're going to be sending data to a process on a different machine, right? And of course, CSCI 330 next semester is a whole semester involved in computer networking, the class, and you learn all about those details about reliable, unreliable communication. It's beyond the scope of this class. And so then there's also the consideration of the logical communication link. And the logical communication link describes the gross level behavior of the two communicating processes at the endpoints of that link. And so you can have direct or indirect communication. We'll talk a little bit more about that, where direct is, as the name implies, that you're communicating directly. Both processes have to be up and running. There's also the converse of that, namely indirect communication links, so that the other process with whom you are communicating, you being a process, doesn't have to be physically running, right? It can come back later, so to speak. Okay. There's synchronous and asynchronous communication. Synchronous means that both processes are running and they execute the call to send and receive, and they block when they do that communication. There's also asynchronous communication, meaning you don't have to wait for the status of the communication, both on the sender or receiver side. We'll talk a little bit more about that as well. There's also automatic or explicit buffering, and that buffering is needed in order to store that message that's going to be communicated. It has to be put somewhere. Now, some buffering is non-existent, meaning that both processes have to be present to receive a message, and some communication links have buffering, meaning that it's stored someplace, and that someplace is memory or buffering, and it has to be allocated or carved out of RAM or some other mechanism. Okay? All right. Any questions about this? So that's where we left off last time. Okay, so continuing on, for direct communication, you have two processes, and the send and receive is not always that particular API call, so you can kind of think of this as a kind of pseudocode that describes what the behavior is for the two communicating endpoints over the communication link. And so you have two processes, and when you have this direct communication, the processes have to explicitly name one another, right? So you have a send method or routine, and some process P enterprises to communicate some message to process Q. So you have some way of identifying with specificity process P and process Q. And that could be a unique identifier. It could be some sort of addressing mechanism. It could be a text-based name. Doesn't matter what that identification scheme is or how it takes form, but nonetheless, process P and Q are identified specifically to one another. And then on the sender side, P gets its message called send, and it has its address, and it uses that to send, when you're sending to process P rather, you use P's address. And likewise on the receive side, when you want to get a message from the channel. So you receive a message explicitly when you want to take that message out of the channel, right? And so if I want to be the recipient of a message that you have sent me, I have to issue this receive command to the channel, meaning a signal to that link that says I'm going to now retrieve one of these messages from that particular entity that I'm describing as Q using some addressing mechanism. And so for these communication links, some properties that you might have, now they don't have to have all these properties, they might have some of these properties. A link is established automatically. Well, that's a nice feature, right? For systems that do that. You don't have to worry, you being the implementer of this communicating set of processes, you don't have to worry about all the details of the link creation. Well, that's kind of nice. And if you think about what happens in a network communication, that happens for you underneath the covers. You don't have to deal with all the details of the management of the pathway along the way between the sender and receiver. The TCP/IP runtime does that for you. Please take computer networking next semester if you want to know a little bit more about that. And so links can be established automatically, and a link is associated with exactly one pair of communicating processes. This idea of a channel connotes that you have two entities on the endpoints of that channel that want to exchange messages with one another. And so this link is defined specifically by the two endpoints. And if you think about it, if the endpoints are named uniquely, then you can have many channels available running at the same time, many links of communication. And so you have a link associated with exactly one pair of communication processes, and between each pair, there exists exactly one link, right? So you don't want to have more than one link. That's not entirely the case in modern TCP/IP implementations, but at the end of the day, it's a good idea to have one link only for each pair, right? Not all systems enforce this, and certainly it's not the case with TCP/IP. So the link may be so-called unidirectional, but for the most part, it's always bidirectional. Unidirectional, that directional part corresponds to the direction in which the data you're communicating passes. And so if you have a unidirectional link between process P and process Q, that means information can only flow, bless you, in the direction from P, originating at P, going in the direction of Q, right? And that's whether or not it's from between two processes in the same machine, or two processes between two different machines, whether locally or across the wide area on a different network someplace else. But for the most part, this link maintenance and the passing of messages is an expensive process. And so it's typically that most links are bidirectional. Now, it doesn't always mean that you can send data in both directions at the same time. Some do that, but it doesn't always mean at the same time. Okay. All right. Any questions about this? Make sense? Yeah. All right. So moving right along, you can have indirect communication as well. Now, with the indirect communication, that means if two processes, P and Q, are going to exchange messages, and indirect means that they both don't have to be active, that means you need some place to store the message. And email does that. You have this pool of storage, and that pool of storage is unique for each identity. It's called your mailbox. And when someone wants to send you a message, you don't physically have to be there. And what happens? Your mail transfer agent on your behalf stores this message in your mailbox so that when you do attach, right, or you do activate the system, you can now retrieve those messages which have been waiting for you. And that's exactly what indirect communication does. You still need an addressing scheme, and this addressing scheme ties the identity to that particular pool of storage or to your mailbox. And so messages are directed and received from mailboxes to other mailboxes, and in an operating system's parlance, it's called a port, right? They have to give it a different name because a mailbox already exists and it has a specific meaning as it pertains to email. So they call it a port, and each mailbox has a unique ID because you have a unique mailbox associated with every user, bless you, identity. And therefore, the mailboxes have to be unique when they're identified to the system, because you're going to have to deliver messages to a unique person. You want to make sure it gets to the right destination. And so processes can communicate only if they share a particular mailbox. And so that mailbox becomes the quote unquote link, if you will, that allows this possible detached communication between two processes. So you send a message for someone, you send it to that mailbox, and that person comes alive, that process, and then it accesses the mailbox and can now get those messages that have been sent to it. And so they can communicate only if they share the same mailbox or that pool of storage, which is serving as the link for communication. And so, some link properties for this case of indirect communication: links are established only if processes share a common mailbox. Well, that seems obvious, right? If the pool of storage over which the messages are deposited are not shared, then you can't communicate in this detached fashion. And so you have to share the same mailbox in order to establish a link with someone. And so you can also, with this mailbox, the nice part is you can have more than one process associated with a mailbox, right? So you can imagine this pool of storage. You have some number of processes, say K many, they all come alive and now access that mailbox. But that multi-point communication, the ability to communicate with multiple processes, comes at a cost. And that cost is, what do you do in terms of the message delivery? Are you going to just send that message to one of them, or are you going to allow the sending of that message to more than one of them? So a link is established only if processes share a common mailbox that allows that multi-point communication, and therefore you can associate a link, a communication between one process, process P, and some other processes, Q, Z, W, X, for example, right? So you can have that so-called multi-point communication. And so with that, you have to decide what it means to communicate. So each pair of processes can therefore share several links, right? You can have several mailboxes and perhaps use those different mailboxes for communication of different types of information. And so a link can be unidirectional or bidirectional, right? It just matters who the intended source or originator of the message was and who the intended destination of that message was. And it's just a matter the person to whom it's destined, or the process to which it's destined, is the one that picks that message out of the mailbox. Okay. Any questions about this? Make sense? So we'll see some examples of this programmatically, but I still have to talk about how it works at a high level first. So some operations. Of course, you have to be able to create a mailbox and destroy or tear down a mailbox. If you're going to do indirect communications, you have to be able to create this channel. And as it might seem, of course, this would take resources because it's a pool of storage. It could be a pool of storage that's backed by disk, backed by memory, or some mixture of the two. So you can create mailboxes, you can destroy mailboxes. You also need primitives or system calls that allow you to send and receive. So the send is the taking of a message and putting it into the mailbox or that storage pool, and the receive is the picking of that message off or out of the mailbox or storage pool. And as a result of doing that, the mailbox should mark that that pool of storage is now available to be used for new messages. Okay, all right. So we have our send, and you are also identifying the process uniquely that executes these. So if process A is going to send a message to a certain process rather is going to send a message to a certain mailbox, you identify that mailbox because the mailbox identity is akin to the process ID, but you identify it by the mailbox instead of by the process. And likewise, you can receive, as a receive call, to receive a message from a particular mailbox. You give the mailbox address A, and then you get back that message. Okay. Any questions about this? Make sense? All right. So you can share mailboxes. So let's say you have three processes, P1, 2, and 3, and they all share a particular mailbox. And let's say P1, process P1 is the sender, and processes P2 and 3 are the recipients. And so one question with this shared link, this pool of storage that you use to store messages, it facilitates or implements the channel, is who gets the message. So if P1 sends to mailbox A, does P2 get the message? Does P3 get the message? Or do they both get the message, right? And those are semantics that you have to be clear about if you're implementing one, or maybe you're using an existing mailbox facility for some application you're designing. So one solution is that you allow a link to be associated with at most two processes. You might limit that idea of two processes, P2 and P3, both being receivers on the mailbox. Well, that's one solution, and it simplifies the problem. Or you can only allow one process at a time to execute the receive. So when the receive call is being made to get a message off the mailbox, no other process can call receive, right? So in effect, that's implementing point-to-point communication between just two processes by locking out all the other processes from doing a receive at the same time. So in that case, if P1 sends and P2 and P3 call receive, and let's say P2 gets there first, its receive system call is the one that arrives at the OS first. So then subsequent receive calls will get blocked and won't be allowed to get messages off the mailbox until the first one that got there is done executing. Okay, so that's one way you could do it. And then another is to allow the system to select arbitrarily which receiver gets it. Now that's a little bit funky, right? Because you want to make sure your communications are guaranteed, right? And you don't want to have any stochasticity as it pertains to message delivery. Another one that's not listed is you could just allow all interested processes that call receive to get a copy of the message, right? And that's a type of multicast facility. Right. Any questions about this? Make sense? Okay. So synchronization. Now, of course, when you communicate, how you communicate comes in two flavors. One is called blocking, and one is called non-blocking. Now, what blocking means is do you wait? Do you, the process, wait when you issue these system calls, whether the send or the receive, associated with message sending or reception? And so when you block, that's considered synchronous, right? So there's the send side of a communication and there's a receive side. When you do a blocking send, that means you have a message and you have a destination for that message, be it a mailbox or directly to a process. A blocking send is one where the process doesn't do anything. It waits for that system call to complete. And only once that system call completes does it continue its execution, right? So it kind of stops at that system's call. So a blocking send is one where the sender is blocked until the message is received, right? So that guaranteed delivery, you can almost say that once this routine to send returns and the process can continue, you have a semblance of a guarantee that that message was delivered to the receiver. That's one of the reasons for a so-called blocking send, a synchronous send. Okay. There's also a blocking receive. What a blocking receive does is any process that calls a blocking receive, it's going to call that system call, and it does not do anything else until that system call completes. Now, completion of that receive means that that message was successfully pulled from that communication link and delivered into memory of the calling process. Okay, so a blocking receive is one where the receiver is blocked until the message is available. Now, that can be a good thing depending on, what your ideas of reliability are for the underlying program, but that can also be a bad thing, right? Because if you have a process that is trying to do a lot of different things, like a browser, it's trying to draw web pages, it's trying to load web pages off the internet, and doing a lot of different things, maybe a blocking receive isn't the right thing for that browser. Unless maybe you're using threading, and we'll talk about threading for the next module pertaining to material from chapter 4. But nonetheless, it's really important to understand when you are programming an application, you're going to be offered by your operating system a number of system calls for interaction between processes, whether it's link-based communication, mailbox-based communication, and so forth. One of the things to ask yourself is based on the behavior, the semantics of my intended program, is it better to block when I do my send and receive, or is it better not to block when I do my send and receive? Because that can make or break the performance of your application. Make the right choice and things are great, but the wrong choice and it's catastrophic. Okay? All right. Any questions about this? All right. So we also have non-blocking sends and receives, or so-called asynchronous communication. Now, what non-blocking means is that the system call, instead of the process stopping and waiting for the system call to complete, that system call is registering something with the underlying operating system, but immediately it returns back to the calling process and it can continue on doing other stuff. So that means at some point, when that communication is either going to complete or something interesting happens, that application or process that called that non-blocking call has to be notified somehow by the operating system, right? So let's talk about this. So a non-blocking send. The sender sends the message, and then continues on. So if you're going to do an asynchronous send, that means that message that you want to send has to go somewhere, and it's the runtime of the operating system that completes the sending, right? So your application has a message, you call that send on the communication link or mailbox, and then immediately returns back to the sender. Now, during that time, what happened? That message was stored someplace in a buffer by the operating system, and the system call and the OS runtime did that for you. And then this runtime says, okay, well, process P intended to send this message, so let me go ahead and send it on process P's behalf. But in the meantime, process P called the send, it returned back immediately to the process, and the process has gone along merrily doing other stuff while the OS runtime underneath the covers is continuing the send process. So in that case, the send is not blocking. The process isn't waiting for that system call to return, and it returns only when the message is delivered. The process returns immediately when it calls that send, that asynchronous version of the send. And it's someone else, the operating system, does that send on its behalf. Okay, so non-blocking receive. So the process, when you do an on-blocking receive, you call the receive call, right? And that receive call checks the status of the link, and either you have a message waiting or you don't, right? It does not wait for the message to be successfully delivered, right? If a message is available, it goes ahead and it delivers that message to the calling process. If no message is available, it returns immediately with a null to say, ah, there was nothing for you. Okay. Now, there are other asynchronous receives where you set up what's called a notification, right? And that's how it's done in most modern incarnations of non-blocking receive. And essentially, you register with the operating system instead of calling receive. You call this registration routine that says, if there's a message destined for me, this is my address, please call this function, and that function exists in my code, right? So you're using callbacks to handle that reception of the message. Okay. Any questions about this? Make sense? Okay, so asynchronous I/O is heavily used in modern web server and modern server implementations. And what it does is it frees your process from making blocking calls. Because as you can imagine, when you're waiting for some event, of course, you being the process, you're taking off the ready queue and put in the wait queue associated with that device. And waiting is expensive. Waiting kills your performance. The more time or percentage of time uh, during which you're running that you spend actually doing useful work, the better the performance of your system. You're being more efficient. Okay, so if you're trying to write scalable applications or you're trying to write very responsive, fast applications, you want to find opportunities to minimize any kind of blocking or waiting that your process might engage with. Okay, all right. Any questions? No. All right. So there are different combinations of this. This doesn't say that you have to have all blocking or all non-blocking sends or all blocking or all non-blocking receives. You can have mixtures of them. And the key question is it right for your application, right? And but know what the consequences are. And then based on your application, what is the correct way to do communication between processes? Okay. So let's take a look at the producer consumer problem. We have this shared communication link, and it doesn't matter what it is. It could be shared memory, it could be a message queue, it could be a network link. And with this blocking or synchronization in general, whether it's blocking or non-blocking, this idea of producer consumer becomes trivial, right? So before we had these spin loops, and these spin loops were an empty while loop that basically caused the process to do nothing, right? It had just a semicolon, and that was an empty statement in a tight while loop. And so we had this check before to see if the location in the queue where the new message was produced was the same as the location from which the consumer was taking a message, right? And we use that spin loop to cause the processes to do nothing until there's a slot available, like there's a message available, or there's a space in which to put a new message on the producer side. So here now we have a producer, and we just have our while loop, the outer while loop from before, and we just send, right? If it's a blocking send, then it'll just stop at that send and do nothing else because it's a blocking send until that send returns, meaning the message was delivered. If it's a non-blocking send, then it'll just call the send and return immediately, and then loop again, call the send and return immediately. So that means each time it calls send and returns immediately, it's giving a copy of its message to the operating system, and the operating system is working behind the scenes to actually deliver that message to that channel or mailbox. Okay. Likewise, on the consumer side, we have just a tight while loop, and we call the receive call. If it's a blocking receive, well, that receive does not exit until the message is delivered locally or taken off that communication link or mailbox. If it's a non-blocking receive, if there's a message available, it'll return it. If there's no message available, it'll return null, and then we just keep spinning in that while loop, doing it again and again and again and again. Okay, and so the point behind these two modes of synchronization, whether it's blocking or non-blocking for communication link access, greatly simplifies your producer consumer problem. And that, of course, was the model that we used to describe two processes, P1 and P2, that are coordinating with one another. Okay. Any questions about this? Does that make sense? Okay. So buffering. Now, certainly, you're going to need a place to put a message, whether it's a mailbox or it's a non-blocking send. You're going to have to maintain buffers, you being the operating system, in which to put these messages. Okay, and so this buffering consideration, there are different ways you can have buffering. One way is to have no buffer, right? Making no choice is also a choice. And if you have, excuse me, a zero capacity buffer, that means that both processes have to be active and running in order to communicate because there's no place else to store the message. So both have to be active, excuse me, on the respective sides of the link to actually physically pass this message and receive this message. So that has a special term. It's called rendezvous, right? Both entities have to be running and they have to be active in order to communicate, right? But the trade-off for that is that you don't need buffering, right? Because you don't need that temporary place to put your message to store it. So if you have perhaps maybe a resource constrained system and you can't afford buffering, then Rendezvous might be a good model to choose. If you have a data center and you want a highly scalable system, Rendezvous might not be a good choice, and it certainly isn't because you don't want to stop processes to wait until the other endpoint is up and running. Okay. The second one is a bounded capacity. Now, bounded capacity is nice because you have finite resources for buffering on any machine. But after so many calls to store messages, so let's say you're doing the non-blocking send, you call, non-blocking send gets called 10 times, that means 10 messages are passed off to the operating system to store. So of course, once you exhaust those resources, what happens when the next process comes along and tries to do the non-blocking send? If there's no buffer space available, it's considered an error message when you try to do the send. So the good part about that is that if you have finite resources, you will never exhaust the finite resources, potentially crashing your operating system. The bad news is the failure is very, very hard. So all of a sudden, it's running merrily along, doing its thing, and all of a sudden, someone comes along, nothing, right? So the degradation is not so-called graceful, okay? But you can still manage finite resources. And you can either have somebody wait, or you could just consider it an error message, and then they try again. That process tries again to do the non-blocking send. Then we also have unbounded capacity. Now, unbounded capacity, as you can imagine, in real systems, you don't have unbounded resources for buffering. But what you do have is you have RAM, right? And then you also have far more, typically one or two orders of magnitude more storage and disk space. And so what typically happens in so-called unbounded implementations, your buffering is implemented in RAM, but then things that it's not actively accessing, it pushes those off to disk. We have a lot more storage. And it gives you the illusion that you're accessing a buffer, but really what you're doing is you're accessing a cache that brings into memory parts of your buffer, which is on disk, and disk is much, much larger storage. And so with this unbounded capacity, you have what looks like, I won't say infinite, a very large, so large it seems unbounded, sized buffer. And as your processes come along and do something like a non-blocking send, the operating system stores it in the buffer, stores it in the buffer, stores it in the buffer. And then this buffering system through the OS kernel now manages which parts of your memory, of your data, your messages are in memory, and which part are spread across the disk. And so this unbounded capacity buffer is nice because you have more graceful degradation. And the degradation goes that once you exhaust enough or use up enough buffering, the performance gets slower, but it doesn't just stop when some new process comes along, which is kind of nice for some systems. And so, which is right? It depends on your implementation. For some implementations, you want to have graceful degradation. It'll allow new users, new processes to send messages, but it just gets a little slower, right? And for some applications, maybe it's banking, maybe it's certain other critical applications like that, it's better to degrade gracefully, meaning the performance slows down as the resources approach being exhausted, versus just stopping. Right. If you're someone like Amazon, well, if it's important to have more customers, you might decide, hey, well, let's have graceful degradation and use unbounded buffers. But if you're someone like Netflix, maybe it's better to disallow someone to be able to stream a video because if things slow down, they degrade gracefully, yes, but the experience looks really bad for the end user, right? So it really depends on your application whether or not your buffers are going to be bounded or if they're going to be unbounded. Okay. All right. Any questions about this? Make sense? Okay. All right. So let's take a look at examples of interprocess communication systems. In this particular example, we're going to look at the usage from the C programming interface, the usage of shared memory, right? And so we'll have some C code up here, and we'll actually pull up Ubuntu on VirtualBox, and we'll actually go through it and show you this. Yes, it does really work. Okay. So this is the command for POSIX, that common Unix API call or system call interface for doing managing shared memory. Now recall, you can use shared memory. I have to concentrate really hard with that beeping. All right. Maybe it'll finish backing up. And all right, well, it's probably not going to stop. It's going to turn into something else. All right, so there we go. For shared memory, first thing you do is you create shared memory, right? Now, shared memory, as I said before, is parts of your RAM that are designated for communicating between processes. So some process has to share that memory, has to create that shared memory. Now, when you create that shared memory, there's the indication to the operating system that this particular memory, I don't want it to go away when I exit as a process. I want it to stay pinned, meaning I want it to stick around, right? And I want the operating system to note that this particular block of memory is off limits for allocation by other processes, right? And the beauty about this is that other processes, if they know the name associated with the shared memory, they can now attach this shared memory to their process and now use it as if it was local RAM for them, but it's really this shared memory. And this is used all the time in imaging processing pipelines for computer vision, because you can imagine, if you're processing or doing some manipulation with, say, a high def image that's 1080, 1920 by 1080 pixels, right? So that's a lot of data to keep writing to disk and allocating and reallocating and writing to disk and reading from disk and writing to disk. So what typically happens in practice is you create shared memory. You load it once into shared memory. The first process that wants to do something comes along, operates on that image in memory, and then that process exits, leaving that manipulated image in shared memory. Then the next process comes along and it operates on that image in shared memory, and then that process exits, leaving that result. So let's say you had, 4 different processes that want to do different things to an image, to say, look at the edges or to manipulate the color or remove the dark spots or the shading or make the image more crisp or what have you. You can have all of these processes come up, execute, manipulate that image in memory, and then exit, and then one last process comes along, takes what's in shared memory, writes it to disk, and then deallocates that shared memory. So it allows you to allocate memory that can exist after the process exits. Okay. So this SHM open, shared memory open, takes three parameters. One is the name, and so all the processes have to know the name of that shared memory segment. And so it also has some bits that control the how it behaves. Well, ocreat means I want to create the shared memory, and then RDRW means it's going to be read writable, right? So you can create shared memory that can only be read. Um, I don't know why you create memory that can only be written, but you can do that if you want to, or you can have one that's read writable. And this is the case for this example. And then these 0666, those are permission bits. If you take these numbers and you look at what they look like in binary, right? 6 in binary is 110. And that those binary equivalents of what these mean correspond to what the permissions are for the user process that executed this command, the group to which this process belongs, as well as everyone else. So in this particular case, this digit represents user, that represents group, that represents everyone else. So that means both the user that executed this can read it and write it. The group to which that user belongs, the account name, can read it and write it, and then everyone else that's not that user and not in that group can also read and write this particular shared memory. So once you create the shared memory, now you have to allocate the size, right? And so it's a little bit different from something like malloc. When you call malloc in one system call, you're giving it both registering with the operating system that you want to carve out RAM from the heap, and you also give it the size, how much RAM to allocate. Shared memory is a little bit different, right? So you create the memory, indicate that you're going to create the memory, and then when you size the object to actually allocate a certain number of bytes for this particular named shared memory, you use this ftruncate command. And so you give it SHM file descriptor, which is the result of opening or creating that shared memory, and then you give it the size for that file descriptor, 4096 in this case, 4096 bytes. Okay? All right. Any questions about this? Make sense? Okay. So then the converse, if you're going to create shared memory, you also have to delete that shared memory. And so once the last process is done with it, on the way out, that process would then unlink that shared memory. And unlink is the system call for doing that. So now any process that wants to use the shared memory, well, if you come along and you say SHM open, you can now attach that shared memory. I'm sorry, mem map. You can attach that shared memory and it appears as if you had allocated it yourself. So now here we have sprintf. Now we're filling that shared memory buffer with some data, right? We're sending the stream version of print. You give it the shared memory pointer, and then you give it the message, and it's now putting that message in that region of shared memory. Okay, so we'll see an example of this, and that's this example. And this example is for the producer, the one that's putting data in the shared memory. And then in the subsequent side, we have the C code for the consumer. Now, it looks a little bit messy because there are comments interspersed all throughout there, but we'll actually write this at the command line and test it out. So we start out, we set some bookkeeping, some size stuff, and we have our number sign includes. And then we choose a name for that shared memory. And anyone who has the name for that shared memory will be able to use it, attach it to their local process. And then we have some messages, in this case, hello and world. Then we have an integer for the file descriptor that we're going to use to identify that shared memory segment when we register to the operating system that we want to do it. And then we create a pointer local variable, and that's void star, because at that moment it's just a pointer to any type of type, but we're going to later assume that it's a char star, right? So that's just to allow us to access from this process that shared memory segment once we attach it to our local memory. So the three routines of importance are the SHM open, so that's to create. It's going to create it, readable, writable, and these are the permissions. The permissions are read, write for both the user that does it, the particular identity, its group, as well as everyone else. Then ftruncate, so it's going to now take that shared memory and allocate 4096 bytes of shared memory once we've created it. And then this mmap, that's where you say, okay, take this shared memory and create it as a memory address that I can access as if I had allocated it on the heap, right? So we have mmap, right? And we have how many, what size of the shared memory segment, what are the permissions in terms of whether it's shared or I can write it or if I can only read it. And then this is the file descriptor for that shared memory. And then I forgot what that last one is. You can actually look up in the man pages what that last parameter is. So then after that, we sprintf into it that 0th message, the hello, and then we increment that pointer, right? Now, when we increment that pointer, we increment it by the size of the data or message that we wrote. And now we're going to fill the rest of that shared memory buffer with world, which was the second message. So we start out, we put that message, this is message 0, in at the location of that shared memory we allocated, and then we increment our memory address by the amount of data we added. So we're now going to the empty part of that buffer, and then we put more data in it, and then we return. Okay? All right, any questions about this? So we'll actually take some time and hopefully can get it done in what remains. Ooh, 10, okay, yeah, 10:45. All right, so now this is the consumer, right? So the producer exited, it created this shared memory segment, it mapped it to its local address space, and it put some information in that shared memory buffer. Once that producer, that first process on the previous slide, exits, that shared memory is still there, right? And it has that message the producer deposited into that shared memory segment. So now the consumer comes along, and this is the consumer, and the consumer is going to attach to this shared memory, map it into its local address space, and then read out that data, right? The producer is now gone. The producer doesn't have to be around. It's now exited. So the consumer comes along, it has the size and it knows the name, and it calls shared memory open. It uses that name, and that name is for a shared memory segment that's there in memory. So it says, okay, to the operating system, I want to associate with it. And here it's read only. I'm not going to write anything. I just want to read, right? So there are protections associated with shared memory segments. And of course, I set permissions for read write for the user account name that called this, the group, as well as everyone else. So now I map it into my local address space. That's the mmap. And now I'm going to print what's at that location. I'm going to access it. Okay. And you'll actually see that same text that was put there by the consumer. And lastly, the consumer calls this unlink, SHM unlink. That takes the shared memory segment and signals to the OS, okay, go ahead and release this memory. It's no longer going to be pinned or persist across processes. It's going to be removed. Okay? All right. Any questions about this? So let's try this out, and I'll try this in Ubuntu, and we'll see what happens. I usually have a printout, but I forgot it on my printer this morning at home. So let me do this and show, and I'm gonna first uh, write the producer, and then I will write the consumer. Oops. Okay, so let me run a virtual box, and I'm gonna put this up on the side, and hopefully, there we go. It's a little bit hard to see. Let me see if I can make this a little bigger. Oops. So people in the back can see. Okay, there we go. All right. So let me run VirtualBox. There we go. VirtualBox. And power on the VM instance for Ubuntu. Oh, this is going to be interesting. Grub the bootloaders on and select Ubuntu. So let me do this. I'll make this over here. Put this over here. I really wish I had my printout with me. That's okay. Okay, so OSC. Tab. I know. Well, that's kind of hard to see, isn't it? No. Can you see that in the back? Probably not. All right, let me do this. All right, so let me just. I actually did it ahead of time. Um, let me just pull up what I did ahead of time, and we'll just go over some of the parts of it. Okay. All right, so clear. So let me go into my directory. Oops, clear. Control C, clear. My processor is working overtime. I think I should minimize this a little bit. All right, Mary Wholeness. Okay, and let me, for good measure, it's called producer test and consumer test. Let me add to the make file to compile these. So I'll add a default rule for producer test, producer, producer test, and a default rule for consumer test. Let me come down here and add rules to compile the C files for both. Producer test.o depends on producer test.c. I'm going to call GCC, compile GCC-C producer test.c. And I'm going to do likewise for consumer tests, consumer test.o depends on consumer test.c. And I'm going to call GCC, compile consumer test test.c. Okay, so now we have to do the link, and the link for this is going to be a little bit different from what we had been doing in the past. It's still using GCC, but we're going to also include another library, right? And that library is different from the plain vanilla library that gets linked in with the executable when you compile without any additional commands. This particular library is going to have the implementation of part system calls having to deal with shared memory, right? So let's see. So let me come down here and let's have a target for producer test. Producer test. That executable is going to depend on producer test.o, the object file. And I'm going to call GCC-O producer test. All right. Producer, oops, producer test.o, and I'm going to say -L, and that says include the library, and the library is called RT, librrt, right? So you're going to need that -LRT in order to use the shared memory API calls or system calls. So we'll do likewise for consumer test, consumer test, uh, consumer test, oops, test, oops, test.o, right? And I'm going to call GCC-O, produce executable consumer test. And I'm going to link in consumer test.o and use librrt, all right, which is for the shared memory stuff. Okay. So let's just call make, try this out, see what happens. Okay. So let's look first at producer test.c. So vi producer test.c. Okay. So I include a bunch of includes, and standard bool.h has a definition for true and false. You don't have to do that, but C doesn't understand what true and false means unless you include standard includes for it. Otherwise, you can just use 1 or 0 for true, 1 for true and 0 for false. So we have a bunch of includes. Standard IO allows you to print things. stdlib has some standard definition string to do size of and string length, and UNISTD for certain standard Unix things. Memman for the ability to call memmap memman.h include. shm.h has the definitions. System shm.h has the function definitions for the shared memory uh, open. And so, you can Google search examples of it and you'll see the includes that you use. To do this. So we have on this line here, we have that size and we have name, right? So name is OS and we have our two messages. Now, const modifier, that just means that this is a constant. It's not going to change. That's one way you could do it. So if you had, int size equals 4096, if it's a const, if you tried to change the value, the compiler is going to tell you, sorry, that's a constant. You can't change the value. So this type modifier called const is one way in C that you can set this idea of a constant. Um, okay, so we have our shared memory file descriptor. We have that void pointer, and here's the call to SHM open. The name is OS and O create ORed with O read write. Now it's ORed because these values O create and O read write, those are constants, right? And when you're ORing them, you're basically turning on the ability or signal to the operating system that it's going to do more than one thing, right? Set the creation, and also it's going to be readable, writable when the OS creates this segment. And so we also have the permissions. Now the permissions I said are 0700. All right, 7 in binary is 111, so that means readable, writable, executable. I didn't do the 0666. You can choose the permissions differently. But for this demonstration, we only really need permissions for the user, account name, or identity on the system that created this shared memory segment for this demonstration. So I added this other check, the shared memory file descriptor, SHMFD. If the shared memory open, that signal to the operating system, if it fails, that file descriptor is going to be set to -1. So I just added a little check just to see, all right, well, if it failed, do I know it failed, right? So it doesn't fail, but it's nice to have that sort of error checking alongside within your programs. So then I call f truncate, right? And I take the result of f truncate. It's going to return back 0 if it's successful, non-zero if it failed, right? And so this f truncate call says, go ahead, now that you have indicated to the operating system that you want to create a shared memory segment, go ahead and allocate it. Now, of course, if for whatever reason, maybe you specified a size that it doesn't allow you to, or it's too big, then it'll return back an error message and not do that shared memory allocation. So for good measure, I just added a check to make sure that the f truncate was successful. Okay. So now we have that M map, and that M map, um, I go ahead and I take that shared memory segment that I just sized to 4096 bytes, and I go ahead and say, okay, now create a pointer to that so that this process running this producer test program can actually put something in there, can read it or write it. Okay. All right. Any questions about this? Yeah? Oh, no. All right. So now I did something a little bit wonky here, right? And I did that because I was tinkering with it and was looping and doing some other stuff. But I take my pointer that I just mapped. So pointer gets the result of M map. So now this pointer PTR is of type void star, and I can use it to read and write. But my practice is I don't like to use the actual pointer that was returned to me. I like to make a copy of it, especially if I'm going to increment it or change it, because I don't want to lose my address of the beginning location of memory. So let's say you have this big block of memory and you have a pointer that points to the beginning of it. If you're going to increment and move through it, I tend to want to leave alone that pointer to the beginning of it. I make a copy and I change that copy, but I can always get back to the beginning of that memory by saving off that original pointer that I got. So I do that, and I have pointer one, and PTR1 pointer one is literally just a copy of that pointer, which is the beginning of the block of shared memory. Right? That's just my practice. You can choose to do something else, but I don't like to modify a variable, a pointer that marks the beginning. I like to have a separate variable that I call the cursor. If I'm going to increment and move through it, I want to change something different from that location, that pointer that gives me the location at the beginning. So I take pointer 1 and I set that to pointer, right? So now I have a copy of the beginning block of memory. I do my sprintf of that first message, that hello message, message underscore 0, into that shared memory. And then I increment pointer 1, and then I go ahead and print or store world, that second message, into the new location inside of that buffer. Now, of course, pointer 1, I say pointer 1 plus equals, right? So that means I'm changing the value and now referring to that part of the shared memory block that's just after where that first message was written. Okay? Any questions? That makes sense? All right. So I'm going to exit this. I'm going to write it. And let's take a brief look at the consumer. VI consumer test.c. All right. So there's my consumer. And, it's pretty simple. Again, I have the size of the shared memory and I have the name. Now, that name is really, really important, right? Without that name, any other consumer can't attach to that shared memory segment. Once the producer runs, it'll persist in memory, but the consumer can't access it without that name. And how you choose to share that name between the producer and the consumer is up to you. In this particular example, it's hard coded in the code of the producer and the consumer, but you could conceivably maybe the two processes access a file and they read out of that text file or configuration file what the name of the shared memory segment is. That's entirely up to you, but they have to have nonetheless the same name in order to access that shared memory segment. So we start out here and we have the name and we have that size and we have an integer for the file descriptor shared memory. And you need that in order to tell the OS which shared memory segment you're talking about. So we have this pointer here that we're going to use to access that memory. And then we call SHM open. So the consumer is going to open that shared memory segment and it has the same name that it furnishes as the first parameter to SHM open. And it's going to be read only. And you notice here the permissions are different, right? Um, in the producer's case, it was 0700. Here it's 0666. We call mmap. So once we access, if you try to access, if you SHM open a shared memory segment that has already been created, it will access it. If you do an SHM open for a shared memory segment that has not yet been created, i.e. a different name, it'll create it for you, right? So this create, SHM open will either create or it will open an existing shared memory segment. So then we call mmap, and mmap then takes the shared memory segment and maps it to a pointer, and it returns back that value in that variable PTR, which is a void star, a pointer to anything. And this now you can use it, allows you, the consumer, to now access what was written in shared memory. Okay. So you're basically taking this shared memory segment and attaching it, and it appears now in terms of the program, you can use it as if you had done a malloc to get this memory. It appears, but it's not actually. So now we do a printf, and that printf, you'll notice here, print what? Print something as a string, and the thing you're going to print is located at location that pointer, and that pointer just happens to be that shared memory buffer. Now here we have a cast operation. You see char star in parentheses that's saying take this void pointer to anything and treat it like a pointer to characters, like a character array, and then it prints it. And so the last thing is this SHM unlink. This SHM unlink says go ahead and operating system, it's a system call, and it triggers the operating system to remove this shared memory segment, tears it down, makes it available for reallocation for some other purpose. Okay. Any questions about this? Make sense? All right, so let's try this out. Now, there's a command in most Unixes, and this command is called IPCS. IPCS gives you the ability to look at various interprocess communication pieces on an operating system. If you said manual pages, IPCS, and IPCS says show information on interprocess communication or IPC facilities. Now, the IPC facilities include queues, message queues, semaphores, and shared memory. So if I said IPCS space dash A, it's going to show me information about all the different interprocess communication resources on the system. So one of the things it'll show me is information about message queues, things like the message queue identifier, the owner, which process created the message queue, permissions, used bytes, the number of bytes that it occupies, and the message number of messages. For excuse me, for shared memory segments, it shows me things like a key, and that's something the OS needs, a shared memory ID, who owns it, the permissions associated with it, the number of bytes, and attached the number of processes that have attached to it, meaning they've called SHM open and they've called mmap, right? How many processes have taken the shared memory and now accessed it so that it looks like it's part of their local memory, because you don't want to delete it willy-nilly if somebody is attached to it using it. And then the status here, if its status is desc, that means it's going to be destroyed, right? And so what this IPCS does is allows you to view the status of various interprocess communication facilities. And then, of course, semaphores we haven't talked about yet. Semaphore is a form of synchronization. So another thing that is available in most Unixes, and POSIX in particular, is the special directory called the device directory. And there's a device directory for shared memory. And it's called, if I do an ls/dev shm/shm. Now, this device directory is something specific to Unixes. Now, in Unix, it has a facility where it treats every single resource on your system as if it were a file somewhere on the file system, right? And the so-called device file system corresponds to that special part of your file system. So it looks like a directory and it looks like it has files in it, but each one of those files in that special device directory is an actual hardware piece of your system, right? And so the device file is a facility that allows you to read the status of different parts of your machine programmatically, and it looks just like doing a file open and a file read. And if you want to control the device, it just looks just like doing a file open and a file write. But underneath the covers, it's going through the IO controller and it's interacting with the device. And that was actually one of the huge contributions conceptually that Unix made. And it wasn't just Linux, it was Unix System 5, which predates Linux by at least 20, 25 years, is that it had this uniform way of treating everything on your system. And that uniform way was treating everything as if it were a file in some directory. So one of the things you can do, if you go to your device file, dev, and if we look at what's inside of the device directory, one of them is the shared memory stuff. I was going to show you the well, yeah. So ls-l disk. So this device file, one of the files in it, if you see when I do this listing, ls disk, is called disk, right? That disk inside of the device directory, that's your actual disk drive, right? And that presents your disk drive in its native form, and that's as a contiguous sequence of bytes, right? Up to however many bytes your disk drive is. And when you format your file system, what your operating system is actually doing is going to dev disk and actually laying out your file system. Now, I'm not saying you should, but if you wrote a program that opened up dev disk, the disk file under the device directory, and you were to just write information arbitrarily there, you destroy your hard drive. Not destroy, you destroy your file system. You'd have to reformat your hard drive, right? And so Unix allows you as a device to access all parts of your system. So let's look at this CPU, and I'll continue on. CPU, right? Cat CPU. I wonder if I can do that. Um, cat mem info. I wonder if it allows me to do that. Nope. It's sys. Okay. All right. Well, I'll stop there. All right, you can access your basic devices. So we'll talk more about that another sitting. Let me go back to the to what I was doing. Okay, so I have producer test and I have consumer test. So let's go ahead and make sure I make. So let's call producer test. Producer test, right? So producer test went through and it wrote hello world in a shared memory segment. Now, of course, ooh, wow, you don't really see that happening, right? So let's take a look at the device file for shared memory. So before we did that, see if I can recall it. Up here in the green, when I did a listing of dev SHM, these were the shared memory segments that were on the system, right? Allocated. Now, let me do a listing again of dev SHM, ls dev SHM. It'll show me the current shared memory segments. And you'll notice here, added to this list is OS, right? And so what this device file represents, it's called a RAM disk, right? It's a portion of RAM that you can access as if it were a file, right? And it's called a RAM disk. And that's how it presents a shared memory segments because it's a portion of RAM associated with a name. So as a convenience, Linux allows you to see them as a RAM disk. And in fact, I could actually show the listing of what's inside of this shared memory segment. So I say cat dev dev SHM OS, show me what's inside of it. Hello World is inside of it. That's exactly what the producer wrote. So let's now run consumer test, consumer test. Oh, we have 4 more minutes. Consumer test is going to go and read it, shared memory, and print it out. And it printed out uh, hello, hello world, right? So if I were to now do the LS, the listing of dev SHM, you notice here OS is no longer there, right? Because the consumer, it removed that shared memory. It did the unlink, okay? If I run the producer again, and I do the long listing of shared memory, you notice that OS is back there, right? Let me run the consumer to print it out, and it also deallocates it. Now, if I run that listing again, OS is no longer there, right? So if I were to run consumer test again, consumer test is going to crash because it's going to try to access shared memory, which has been deallocated, and it crashes. All right, again, it's what's called a segmentation fault. It's trying to use memory that doesn't belong to it. It's no longer there. Okay. All right. Any questions about this? So that's a demonstration of using shared memory. Producer test and consumer test, I ran them separately. They're two different processes. I ran producer test. It sent something to this shared memory link and then exited, right? Then consumer test, I ran that. That process attached to this shared memory and then read something out of it and then tore down the mechanism. Okay? All right. Any questions about this? Make sense? So you can imagine if instead of doing producer tests and consumer tests that just print, put hello world in shared memory and then read it back out, imagine if they were two different processes. One took an image and maybe eliminated the noise or changed or lightened some of the colors or computed the edges in the image or something. And then consumer test was another process that did something else. Or maybe it took an audio file, bring it into memory, put it in shared memory, eliminate the background noise, and then write it out. Right? You could do that in two separate processes through shared memory. So it's not just the examples hello world, but you can use it for anything that you can store in memory, which is just about it, which is anything. Okay. All right. Any questions? No final questions? So if no final questions, I'll end there. It is 10:43, and we'll pick back up with uh, network communication on Tuesday. So I'll see you on Tuesday. I intend to. No, I already did. Wrong class. Never mind. All right. All right. So I'll see you all on Tuesday.